Hello guys, welcome to this short video walkthrough on interactive forecasting of global temperature using exponential smoothing time series algorithm. Our objective over here is provided we are given a list of countries and their corresponding state and the average temperature of the state. Can we predict or forecast the temperature for the next 6 months? So let us see how the data looks like. We are given a list of country over here, say Brazil, Russia, United States, Canada, etc. And for each of these states, we also have their corresponding states. So if I were to change from Brazil to say China, you can see that the list dynamically filters and we get the states or provinces of China. So let us try to figure out how to do a forecasting of monthly temperature for the Fujian province. So now we have a raw data view over here. What we are given is the average temperature from 1841, the first month of January, to the last month 2013, the ninth month, or the September. You can also notice a missing value over here. And let's look at the basic information. What you can see over here is the record starts from 1st of January or January 1841, and the record ends on September 2013. The minimum temperature that has been recorded during the period is 6.32 and the maximum temperature is 29.68. The number of records that we have in the data set over here, as you can see over here too, it's 2073, and the percentage of missing values, as you can see over here, is in total 0.1%. So next look at the interactive time series plot of average temperature. As you can see over here, this is a plotly curve that has a plotly diagram that has been built in R-Shiny, and this shows as you hover over the graph, you can see the temperature change with respect to the months. If you want to zoom in and have a better view, you can also do something of this sort, and you can see the zoomed in view of these interactive time series plot. Next, look at this how I have split the data. The data is split 1820. So as we have seen, the first recorded observation is on 1st of January 1841, and our time for our training set would end at 1979 on the second month, that is February. So that is 1658 entries, and the rest 20% of the data set is the test set. As you can see, the test set over here starts at 1979, the third month, because that would be the month that is next to 1979, second month in the training set. And also, as the last row of the testing set would be 2013, and the ninth month, that is September. So that is the data set that is split into 80-20 in terms of training and testing. Now let's look at the modeling. So in order to do the modeling, let's action button, click for modeling, and you can see over here that there is a process running. The model building is taking some time, and I have approximately seen that it takes around 6 to 7 seconds for the various combination of countries and states. So let's look at the various plots of the time series for China and its state Fujian. Now, what we look at is first the decomposition of the time series into additive model and the multiplicative model. As you can see over here, the additive model corresponds to a combination of three components: seasonality, trend, and random part, that is added together. In the multiplicative model, the same three components would remain, but there is a multiplication done amongst them. So let's look at the decomposition of the plot. The three main things to look at when we are seeing a decomposition of the time series plot is the trend, seasonality, and the randomness. So first, let's look at the randomness of these plots. So for the additive model and the multiplicative model that you can see over here, they almost look similar to one another. And let's look at the stationarity of the time series. The stationarity of the time series is basically a way of finding out that with respect to change in time, does the mean and the variance of the time series change or not. So as you can see over here, a simple eyeball test shows us that there is not much change in mean and variance with respect to time. If you want to do a statistic to confirm this hypothesis, there is a test called the augmented Dickey-Fuller test, where the null hypothesis is that the time is non-stationary, and the alternative hypothesis obviously would be that the series is stationary. Now, if you can see the augmented Dickey-Fuller's test p-value, it gives us a value of 0.01, meaning that the time series over here is a stationary one, confirming our eyeballing test from here that the time series looks fairly stationary. Now, let us also look at the seasons and the months and how they look through. As you can see over here, the seasons and the month over here, the highest temperature is reached in July and August for almost all of the years. And also the graph over on the right side shows us that what is the variation of temperature for each of these months. So you can see that in January and December, there is a large variation of temperature, and during June, July, and August, there is rather a tendency of temperature not varying so much. Now let us next look at the correlograms. We have two graphs over here. On the left, we have the autocorrelation factor plot, and the right, we have the partial autocorrelation plot. The autocorrelation plot or the ACF plot over here shows that there is a periodicity of this in this time series, in the sense that we can see spikes at 6, 12, 18, 24, and so on. So there is an effect on the present temperature based upon the temperatures of, there is a strong effect based upon this first, second, fourth, fifth, sixth, seventh, and so on, because these are the lags that mostly affect the temperatures. Added to that, when we see the PSCF plot, we also see that the first lag has a significant effect on the present temperature. The second, third, fourth, fifth, sixth, seventh does have. Up to seventh we have. Eight doesn't have any effect because it is within the blue dotted line, and so on. So we can see that what we can see over here is that the lag temperature has a dampening effect on the present temperature, and this is one of the reason why we will be using an exponential smoothing time series effect modeling to do it. Now let us look at the parameters of the exponential smoothing model. What you can see over here is that the exponential smoothing model is characterized by three parameters: ETS, which over here means error, trend, and seasonality. What you can see over also is that the error over here is A, meaning that it's an additive error. Also, we also have the the trend as none, and the seasonality as again an A, meaning the seasonality is additive in nature. The way we have set up this model is that we have set up the model with all sorts of combinations that the model can take up with respect to the additive, multiplicative, and the non-component in terms of ETS. And we all have also made the set up parameters as null, meaning that it can take up all sorts of values, and the values for which the AICC is the least would be the one that is actually chosen as the best model. So what we can also look at is the alpha parameter. The alpha is the smoothing parameter over here, and it is over here 0.04. The alpha parameter is basically a smoothing parameter or a weighted average of all the observations from YT to Y1, provided we are doing a forecast of YT plus one time period. The alpha over here is very small, meaning that large weights are given to the distance observations that can be reflected over here. You see that the distance observations have correspondingly have substantially more weights over here. Added to that, the gamma over here is the Holt-Winter parameter for seasonality. This value is very low, as you can see over here, and because with the time that because as time passes, the seasonal variations hardly changes. That you can see over here that as the time passes, there is hardly any change in the seasonal variation. So that would be the understanding of the parameters of the exponential smoothing time series model. Now let's look at the model testing part. Let's go up and click on the model testing part. So the model is being built right now, and let's see. Okay, so the model has been built, and what we are doing over here is comparing between the actual and the predicted temperature. They look fairly close to one another. In case you would like to have a closer view of say one time, one period or 1 year, this is how the temperatures look like. So if you zoom into the graphs, you can see that the predicted temperature uh, for July 2012 is 27.82, and the actual temperature is 28.48. They're fairly close for a lot of other points. You will see that they're fairly close to one another. So this is how the model performs on the data set of 20% of the actual data set. And let us now look at the forecasting. So let us do the forecasting over here. It will take a couple of moments, so let's wait for that. Yes, now that we have the forecasting, what we have seen up till now is our data has ended on 2013 ninth month, that is September, and our forecast should start on the 2013, the 10th month, that is October over here. I'm trying to do a forecast for 2 months over here, and you can see that the point forecast is 21.18 for October, and 2013 November it's 16.37. We also have the confidence value at 80 and 95% confidence interval. In case you would like to have a point and confidence value forecast for say 4 months, we can also do that by sliding the slide bar over here. Let's wait for a moment to find out the forecast for the next 4 months. So now we have the point forecast and the confidence interval for the 4 months, as you can see over here. It's for October, November, December, and January. So this is all from my side for today in terms of how to forecast global temperature with exponential time series modeling. Um, the codes are in GitHub, and I will post them over in the video description. And thank you for your time. In case you have suggestions for me, please let me know at my GitHub and at this YouTube channel. Thanks for your time. Bye.